Hello, everybody. I'm Sean. Um, I work in the electrical power industry. I'm in uh, transmission with a major utility in the Northeast. Um, I'm making this video to kind of, well, there's myths out there that whether which side of the argument you're on, you're not getting the full story. Before I get into that, let me give you a quick background. All right, the power in the United States and all in North America for that matter is set up on an AC alternating current grid. You have your generation station. It produces the power no matter what kind of generator it is. I don't care if it's a solar farm, if it's a wind farm, if it's a conventional coal-fired unit, a natural gas unit, a nuclear unit. Doesn't matter how the electricity is being produced, but there is a generator producing electricity. The electricity gets goes through a really big transformer. It's a step-up transformer to take the efficient voltage of the generator, and then step it up to the high voltage needed to put it on the transmission system so that you can push the power from where the generation is to where the load is. Okay? Then once you get it to where the load is, then there's a step down transformer that'll take these ridiculously high voltages, step them back down, and then go into like an industrial customer that would use a higher voltage level, for example, and then down into your industrial customer, maybe like a mall, and then on down. And actually, let me get rid of me, and down into your distribution level, which is like what your homes, your residentials will be. Okay, so you have the generation, the transmission, and the distribution are your main three. The red is your color codes up here, right? Um, the reason why you have to do this is to push the power. You want to reduce the losses, so you step up the voltage really high because the power stays the same. Once you get the voltage really, really high, the current that is passing on these lines becomes very, very, very low. The lower the current, the less electrical losses you have just in pushing the power the hundreds of miles it takes to get it from a generation to the end load to customer. Okay, that's how the AC generation works. Um, we have and this is in kV kilovolts. So 765 kV is 765,000 volts. 500,000 volts, 345, 230, and 138. There's also a 115, which is essentially does the same, but your 230 and 138 or 115, that's your work. That's what most of the power is doing as it's making a loop around your city, for example, and then it gets stepped down into sub-transmission voltages that industrial business customers, and then step down even more for residential customers, right? So they can be used. The 765 and the 500 are your main. It's kind of like the interstate highway, right? This is what's getting that's what's doing the main pushing of power, getting it from the generation to the distribution, right? Your 345 is it's also think of this more as a state road. This is your interstate, your 4-lane, 8-lane interstate, that's really pushing all the power to transport it. Then you're getting it down in think of this as the U.S. state road system, U.S. system and state road system. This is your Route 92, your Route 52. This is the smaller road, but it's still mainly for transit. Your 230 and below is actually tying in substations within your city to actually make the grid more resilient and make it work so that if you have to take out a line for maintenance, you have an alternate path that can still keep everybody energized. Okay. And then you get it to your distribution, right? Your customers, people actually using the power to turn on the lights, to run pumps and motors, to run equipment, motor generators, in your home, make the heater work, make the TV work, make the toaster work, the refrigerator. Okay. That's in a nutshell the grid. Okay. These transmission lines are very, very important because if you take out a transmission line, whether lightning strikes the insulator and causes a power outage, whether a tree falls on the line, whether a transformer just that's within here, like any substation transformers, through age and through whatever just fail, they break. There's numerous things that can cause these outages. So if you're taking out the transmission line, then all of this really doesn't matter if you can't get the power from the generation to the load. So the transmission lines and the reliability of those lines are extremely, extremely important. Reliability being the key factor. All right. Doesn't do any good if it's free if you can't get it from here to there. Okay. So keep that in mind. Reliability. That's the number one key. Okay. Now, with respect to renewable energy, a lot of people think wind and solar. There's a bunch of other types. Those are the two bigger players in the renewable market right now is wind and solar. Um, First of all, guys in my position, I'm one of the few jobs in the electrical industry that cares not about money. My whole job is reliability. I have the authority to stop work if, let's say, you were working on this transformer and you needed to switch it out of service so that the guys could go in and do maintenance on it. If taking this transformer out of service causes reliability issues on the grid, so that if you lost the line, now without this outlet for the power to flow, you're going to overload other lines, or many other voltage collapse or any of those scenarios, I have the authority in my position to cancel this work, reschedule the work, have them do it a different date, recall a job. Let's say this is already out of service for work. Lightning strike took out a line, a tree fell on a line, took out a transmission line, and it's in the same area as this work. I have the authority to make them stop what they're doing and restore this back to service to put the grid back in a stable spot. All right. A lot of what I do as a reliability coordinator stems from the 2003 blackout, where basically all the Northeast, 50 million people went without power. Well, that really woke up the government and the electrical industry in general, and a lot of changes were made for a reliability aspect. Okay. Now, all that being said, when you talk about wind and solar, you're talking about a very, very, very small portion of the grid. Okay. Now, this information is not classified. It's not secret. It is public information. This is in real time as we speak on 3/23/2002. It's about 6 in the morning. This is PJM, who is an independent system operator for the Northeast. PJM and New York ISO are the two big major covering the Northeast. New York ISO is New York itself, upstate New York, New York City, and then up into Canada a little bit. PJM covers, you can see this footprint, Indiana, Michigan, all the way east. It goes down into before you get to the Carolinas, Virginia, West Virginia, Maryland, Pennsylvania, New Jersey, part of New York, mostly New Jersey, Ohio, Virginia, West Virginia, Pennsylvania. So this whole northeast part is PJM. Okay, then New York ISO. This is their market, which shows what the pricing is, and I'll talk about that here in just a second. But New York ISO is more, for New York State, right? So New York and PJM is pretty much covers the entire northeast of the United States, which is a huge electrical load. Now, this is the generation fuel mix right now, total supply at 6 in the morning on 3/23. In the PJM footprint, there's a total of 76,679 megawatts being generated. Total. Of that, only 6,711 are renewables, and that's all the renewables. Anything that qualifies as renewable: wind, solar, hydro. We call them trash burners in the industry, but because that's literally what they are. But in anything that's considered a renewable resource is 6,711 megawatts in the PJM footprint right now, total. Which where's gas, coal? Here's wind. Is this green? That's wind. Okay. Solar, you can't even see it. I have to blow it up to do it, and I'll do that here in just a second. And then other, you can't even see that too, right? Here's all your renewables, 6,000. Now let's go to New York ISO's footprint. Then this is a little bit bigger, but their total for all of New York is 12,116 megawatts. Of that, only 4,000 of it is renewables. And that's, again, all renewables. And you can see, especially in New York, because, a lot of the, If you take hydro out of the mix, which, because again, when most people think, they're thinking wind and solar, in New York, only 4.49, so 4.5% of the entire New York ISO footprint is wind. They don't even show solar by itself. And then 1.97 is everything else, all other renewables, right? Hydro is 25% of New York's fuel mix. You have natural gas, you have nuclear, dual fuel, which essentially is coal, oil, fossil fuels, as far as what the news reports and is that they villainize a lot. Natural gas, I don't know why environmentalists aren't happy about natural gas. It is extremely clean burning. It is extremely abundant. It is extremely a good fuel for generation. The one thing that a natural gas CT, which is a combustion turbine, nickname is the CT, is how it's kind of abbreviated. It doesn't like cold. It needs to be insulated well against cold. So when it's not winterized well, they don't do well in the really extreme cold. That was the problem. One of the main problems that Texas ran into with this past winter, with a lot of their generators not being able to come online. So when their wind went away, they have a big part of their portfolio is wind. When the wind quit blowing, they needed the generation to come online, and the fuel lines froze. There was a bunch of other things that froze as well. But essentially, their generation fleet weren't winterized well. You can winterize them well because, again, New York, PJM, up into Canada, have tons of natural gas CTs. So it can be winterized. It's just Texas only sees those extreme temperatures once every blue moon. This blue moon kind of caught them with their pants down. They should have been more, had their units more, required them to be winterized better than they did. And now that's a extremely complicated thing boiled down to a 30-second explanation. So trust me, there's a lot more into it, but they didn't have the fuel they needed when they needed it. So again, this is the PGM footprint. You're talking an extremely, and this is all renewables, right? So now let's go to the renewables section and we'll stick with PGM. Here's wind, 4,800 of the 67 megawatts, 4,800 of it's wind. Solar is only 400, not 1,000, 400 megawatts, 481. Hydro is 1,431. So wind and hydro are the bigger player of the renewables, and then all the other renewables don't even show on the graph. So anyone who tells you that we can go completely off the grid with wind and solar is lying to you. Current technology, as it sets now, it physically cannot happen. I don't care what law is passed. I don't care what, it doesn't matter what anyone says. It physically cannot happen. Wind and solar cannot run our grid. If we were to go to wind and solar and renewables only, buy a bunch of candles. It physically cannot happen. It is an impossibility. Now, one of the main reasons why, from my job standpoint, the reliability standpoint, that we are not big on wind and solar is that on top of the wind can quit blowing, the sun cannot shine, and then you have to have other avenues of storing that energy that was created when the wind was blowing and when the sun was shining, and there's a couple different ways to do that. But once the wind quits blowing, if you have all of your, if you've got relying on wind farms, which is what Texas has, like 40% of their power from wind, huge amount of power. Wind quit blowing caused massive issues because when the other generators couldn't come online to take care of the load, it caused blackouts and customers lost power. The main reason why wind and solar, and again, I'm stressing with current technology, is because they don't provide voltage support. Okay. Let me show you this real quick. This is what's called a pump storage facility. I mean, hydro, a dam, a river dammed up is a common, anyone already, that's an easy grasp of hydroelectric power. Another version of it is what's called a pump storage facility. Literally, think of it as an upper pond and a lower pond. Now, these things are huge. They can be lakes. They can be massively large. But the generator is here, and it is both a pump and a generator, all one unit. So during the day, when the price for power is high, and it costs more per megawatt hour, They open up the valve, let the water in the upper reservoir just through gravity fall down this, what they call a penstock in the tunnel, goes through the turbine, turbine spins, generates electricity, electricity goes, good to go. At night, and it fills up this lower reservoir, the lower pond. At night, when the price for power is lower, they turn this into a pump, and they pump the water from the lower pond up to the upper pond to fill this back up so that the next day that they can do this repeated cycle. The net difference between the power they use to pump the pond up and the power they use to generate, the price difference between the two allows this to make money and allows it to be a economically viable solution to generate electricity without having to have an entire river stream. All you have to have is a higher, a mountaintop, a hill, whatever, where you've got a higher level here than you have here, and you're sticking a generator in between. It's called pump storage. It's been around for a long time. There's lots of them. They're great. They do a great job. Okay, this is totally renewable, totally using water, but it can take up a large footprint depending on how large these ponds are. Obviously, the bigger the upper reservoir and the lower reservoir are, the more power can be produced, as well as the least amount of time you have to fill this upper pond. If this is a really, really, really big lake, then you may be able to generate for a day or two before you have to pump water from the lower lake to the upper lake. Okay, that's pump storage. Now, there's a lot of other things with hydro that are going along. It's a really cool, fascinating subject. Now, this is just a picture I got off the internet because I can't really show you what where I set, but it's something very similar. Your operators are sitting here with multiple screens, and this is what we see as the entire grid. This is showing, I believe this is New York ISO's control room. But we're looking at the entire grid as a reliability coordinator in order to keep everybody with power, right? Now, keeping the grid stable and reliable is the goal. That's the main part of our job. I don't mean that absolutely everyone has to have power, because in the worst case scenario, if you have to choose between letting a neighborhood be blacked out in order to save the grid, that's what we would do. There's a lot of levels before you get to that level, but that's extreme cases. But we're sitting in a control room 24 hours a day, 7 days a week. This is never not manned. You have backup control rooms, so if you had flooding or an earthquake or lightning or fire or whatever, you have a backup facility that you can do this same job at a different facility in a different location that is fairly close by, so that you can transit to the other. Or some entities have two control rooms, and they do what's called an active thing, where one backs up the other, and you have two control centers not in the same physical area, so that if you lost one, the other's already there, and it just takes over for the one that was lost for whatever reason. Okay, now back to pushing power. There are three different what's a better way to give you if you think of just a normal geometry, you have a right triangle, 3, 4, 5 right triangle, for example. You can all the power is pretty much explained with this triangle and the math of it. So you don't need super high-end calculus to understand what's going on. You have your true power, which is in megawatts or kilowatts. This is your watts. This is what does real work, is the power on this side of the triangle. You have reactive power, either in MVARs, megavolts, amperes reactive, or kilovolts, amperes reactive. This is the power that's consumed by magnetic fields. And then your apparent power is MVA, kVA. This is everything. This is your total power produced. Now, yes, that's math, and it's kind of crazy. This is your voltage support. This is what supports the power so that it can be pushed from the generation, back to that other, right? To allow power to be pushed from the generation to the load, you have to have voltage support, right? That's this part of the power triangle. This does not do any real work. All this is the magnetic fields in motors and generators and capacitors and inductors. This is the power that's used up by those magnetic fields. So this is your voltage support. This is your true power. Now, let me break it down so that if you have absolutely no issues with, no industry knowledge at all with this, I'll explain it to you. Here's the easiest way that I found to envision what reactive power is. Your job is to get this ball to move from point 1 to point 2. It's on this incline. You got 3 guys. You're going to push the ball from this side of the incline to the other, but you don't want to fall down. All right? The guy's pushing the ball from this side from point 1 to point 2. That's your megawatts. That's doing the real work. That's what's turning the motor. That's what's turning the fan. That's what's making the pump work. That's what's actually doing the real work. This poor guy here is your megavars. That's holding the ball up so it doesn't roll down the incline and, go away. He's holding it up to allow the megawatt guys to push it from point 1 to point 2. That is the easiest way that I can do it from just a total layman's explanation between megavars, megawatts, and then your MVA, which is your total power, right? Your complete power. That's your power triangle. Without this voltage support, you cannot get real work done. Now, the reason I said that and the reason I brought this up and to show you the power triangle that I showed you just a minute ago is, right, there's your power triangle. The reason I showed that is, going back here to good old wind and solar, right? Wind can, their units can provide reactive support, i.e. voltage. As a general rule, the vast majority, 75-80% of them, do not. They provide. Current technology, solar provides none. Cannot. At its current level, there's plenty of research being done. They're working on it. They've got some irons in the fire to get that going to where solar power can give you reactive support. But right now, as it sits currently, you're not getting anything from solar. Without voltage support, you cannot push power from the generation to the load. Right? That's back what, the original, without voltage support, none of this can happen. You cannot have transmission lines, and you can't have generation stations in the Great Lakes, for example, in Lake Erie, Lake Superior, whatever, where they have a nice heat sink from the lake, and power up people in New Jersey. You can't push it without voltage support. That's what causes blackouts. When you have a voltage collapse, that's what has blackouts. When you're here in California, they had brownouts, and in 2003 when you had the big blackout, it can be caused by a number of factors, but what it boils down to is no voltage support. You can't push the power, so you can't get it from the generation to the load, and you have a blackout. Now, again, this is a very, very, very quick explanation, but without voltage support, it matters not what your generation is doing. It could be free. It could be Star Trek beamed in from space power, but if you can't get it from where the generation is to the load, none of the generation doesn't matter. I don't care if it's coal, nuclear, wind, solar, gerbils running in a cage to spin the turbine. Whatever it is. Without voltage support, you can't get power from generation to the load. Period. That is a fact. That is not, there's no argument. It doesn't matter. Now, where wind and solar lack is that reliability. And now look, the guy in my job and the other people in the control center, I would love for wind and solar to be perfectly reliable. Again, my job doesn't care about money. I care about reliability. My job is to keep the lights on for everybody, to keep the grid stable, to keep the grid. So if you have something trip off, it doesn't block everything else out because you had a voltage collapse or you overloaded a line. And then that line overloading, tripping out, causing a voltage collapse. Everything eventually goes to voltage collapse when you have a big blackout. Individual lines can be overloaded, but the blackout where you lose an entire state or an entire region of the country, that's a massive voltage collapse on the transmission grid. That cascades and knocks everything else out. So when you hear politicians say that they're going to have half of the, 60% of the power in this area is going to be from renewables, they're lying. You can't do it. Right now, physically cannot happen. I just showed you the numbers, and like I say, those are real-time numbers. This is not something I made up. This is current, right now, PJM's footprint. That's what it is. Again, this is 6:37 in the morning. That's the footprint. So I'm not trying to scare you. I'm just saying when they tell you that it's going to have 50% by renewables, they're lying. It can't happen. Now, if some magic technology gets unlocked out of Pandora's box tomorrow, great. As it sits right now, can't happen. Now, the other thing that a lot of people won't talk about either is the turbines. The wind, a solar, a wind farm, has these individual turbines. You've seen pictures of them. The newest out, I believe, the biggest turbine you can get now is a 10 megawatt turbine, maybe a 15. Siemens has done a lot of research in getting, but GE has a whole arm of their massive production company that makes turbines for the wind farms. But the majority of them that are already out and built and giving power now are of the 2 megawatt variety. 2 megawatts. A big nuke plant or a big coal power generator can be 1,000 to 1,500 megawatts. Just one. Each turbine, most of them that are out there now, are 2 megawatts apiece. You do the math on how many wind farm turbines you have to equal one power plant. Does that make? I hope that's kind of making sense. Natural gas is great, and we've got the big bulk of our grid right now, at least in the Northeast. A huge portion of it, around 40-50% of it, is natural gas. Natural gas burns super clean. It is close to being as green as you can get, except its origin is from oil. Where the oil is, the natural gas is, as a general rule. But as far as using it as a fuel, it burns extremely clean. It's a great fuel. So environmentalists should be very happy with natural gas. They just are unhappy with its origin and how you got to get it, because it's it's in the oil industry. Now, this is the U.S. Energy Information Administration's website. Okay, and it has what is the U.S. electricity grid by source. Right now, fossil fuels in the entire United States is 60.8% of the grid. Natural gas, as I said, is almost 40, just natural gas. Coal is 21.8. Then all these others are broken down. Then you got nuclear at 19, basically 18.9% is nuclear. Now renewables, total, all the renewables together, wind, hydro, solar, photovoltaic, solar thermal, biomass, wood, landfill, municipal solid waste, other biomass waste, geothermal. But all this biomass section, that's what we call trash burners in the industry, because that's essentially what they are. The waste products are being burned. That is generating heat to cause steam to turn turbines to make electricity. And it's minuscule. It's nothing. All the biomass total is only 1.3% of the grid. It's a nothing burger. Geothermal is 0.4. I'm a big fan of geothermal. Maybe, if you're in the right area and it's expensive, but the concept is very cool. Look up geothermal. It's pretty cool. Pump storage, hydropower, again, other sources. So, again, wind and solar, but 6.3% is hydro, right? So 9.2% is wind, 6.3% is hydro. Solar is only 2.8. So you're talking 20% is total. All the renewables together is only 20% of the grid. That's the entire United States. Some areas are more heavily done in renewables. Texas, for example, for the ERCOT area, it was very heavy in renewables. New York has a lot of renewables, a lot of it hydro. Just naturally where they're at, there's a lot of water ability to make power out of. The PJM footprint has a decent amount has more solar than they have, or has more wind than they have hydro. But again, what it boils down to, 60.8% of the grid is fossil fuels. This is the entire United States, not one area or the other. I'm more familiar with PJM footprint because that's the areas I've worked in. Um, Renewables 20%. And like I said, that's not a pie in the sky. That's not, next week. This is right now. So when a politician tells you that they're going to get so much power out of the grid from wind and solar, can't happen. If it was free, it still can't happen because you'd have to build all of this and then make the power line connections and get them to the transmission so that it can, and all that takes a ridiculous amount of time. You've got to get building permits to run it through somebody's backyard and then no one complains about it, which we all know that's not going to happen. So all your public utilities, your PUCOs, you have to get blessings from that public utility commissions before you can run transmission lines through their domain. That part of the country that county, that state, that city. You have to get permission to run those lines through. All that process takes a lot of time. So there's more to it than just saying, oh, well, we'll just build a wind farm and plug it in. It doesn't work like that. Now, one other thing just to touch on is the price of power. We call it LMP in PJM's footprint, locational marginal pricing. And again, this is right on the website. This is just pgm.com. You click on, there's wire.pgm.com. It's pgm.com. It's right there. Okay. This is a normal day. PGM, this $20 to $40 per megawatt hour is a normal price for power. So, and that sounds kind of funky, but it's literally just straight math. If you have a 100 megawatt generator, regardless of fuel type, and you're getting $20 per megawatt hour, 20 times 100 times however many hours it's running, that's what you get paid for the price of power. Every day, generation bids into this market. Okay? Let me say that again. Every day, because this is a commodity, just like orange juice and pork bellies, and it's like what's on the stock market on the commodity section in the stock. Power is one of those. PJM regulates it. It's not on the stock market. It's in PJM's footprint. They regulate the price of power. Now, if you have a lot of outages where you can't get power from the generation to the people, then this goes up. So if you say, I own a generator, but my cost for running that generator, I can't make any money at $20 to $40 a megawatt hour. So they bid into the market, let's say at 70 to 100. Let's say it's $75 a megawatt hour. So they say, hey, PJM, I have 200 megawatts of generation in this area, let's say there. I don't even know where that's at, but let's say right there. I got a generator. If you need me, I can come online, but I need $75 a megawatt hour. That's what I'm bidding in at. That's what I need to run to be able to make money. Now, through the course of the day, there's outages, storms go through, lightning strikes, takes out a line. Now, this price will change. This graph will change. It changes daily throughout the day, right? If PJM now, to get everybody power, needs this generator, they'll pay them their $75 an hour. They're going to go with the lowest price, PJM is, using the generation that's cheapest first. As things trip out and things go wrong, then these other units get called into at the higher power point, at the higher price points. Now, the reason I say that is, and I'm not picking on Texas. I swear I'm not. We have part of our company's resources are in Texas. Okay, I'm not picking on Texas. It's just fact. This last winter, they had an LMP as high as $8,000 per megawatt hour. $8,000 per megawatt hour. Okay, guys, do the math. If you have a 100, just a little tiny 100, that's not a big unit at all, megawatt unit times $8,000 per megawatt hour, and you run it for 12 hours, half a day, $9,600,000 was the price for power when ERCOT's stuff collectively hit the fan. Now, what Texas has done, is in all its infinite wisdom, and hopefully they're going to do more, but they've passed a law to cap this pricing. So it can't get to 8,000 megawatt, $8,000 per megawatt hour. It can't happen anymore. That's now against the law. I think it's 1,800 or 2,000. But let's say 1,500. And now this has happened in the PJM footprint. $1,500 per megawatt hour has happened in the PJM footprint in a not so distant past. Okay, let's use that same 100 megawatt unit times 12, half a day. $1.8 million for that one generator. That's a tiny unit to run for 12 hours and provide power. Okay, guys, I'm not making this up. There's the pricing. To 500, greater than 500. Let's say 500. Let's go to that. $500 per megawatt hour times that same little 100 megawatt unit times 12 hours. Again, half a day. Not even talking about a day. I'm talking about just, let's say, sun up to sundown. $600,000 for that one generator to run for 12 hours. During peak load, let's say. You need it from sun up to sundown. Till you got the lines back. Now let's talk about one bigger unit. Let's say a 1,500 megawatt, let's say a nuke unit, a big coal unit, one of your larger capacity units. Times the 500 times 12. Again, 12 hours, $9 million. So when the price for power, it's just supply and demand, guys. Again, this is supply and demand. When lines trip out, when transformers have blow up or have a fire, or a generator trips offline because of internal problems, you lose that. Load didn't change. The amount of people with their lights on did not change. So that generation has to come from somewhere else. Generation has to match load. Okay? It's literally that simple. Your generation has to match load. When load goes up, if more people turn their furnaces on, the generators have to ramp up to provide more power. There isn't it's not a battery. There's not a surge volume. There's not a tank, a plug in the wall that you can just produce as much power as you want. It gets stored in a wall somewhere. And then when you turn your switch on, it shoots. No, this is a constant struggle back and forth. They're matching power to load. Again, and I'll go to PJM. Again, this is not anything secret. This is on their website. You can look at it. Okay, data. Now, that's LNP. Let's pick. Let's just do this. This is a graph of generation and load. This is how PJM keeps things balanced. When as load changes, generation changes to match that load. You want to ideally keep this graph needs to be at 0. So you can see it's very symmetrical. It'll have a part where it goes up, but then it comes down and up and down. And it's a constant balancing act between generation and load. Now, this is for the most part automated, where as load changes, the PJM software senses that and sends signals to the generators to either ramp them up or slow them down in order to ramp up or push down their generation for megawatts, right? So this is a balancing act that it does, and it's literally PJM is all the balancing authority for the Northeast, for the bigger utilities. They pay PJM to do it for them. And PJM keeps up with the interchange between who owns the generation, who owns the power lines. They do all the leg work, the grunt work in getting the power from the generation to the load, and it has to keep this basically as close to 0 as you can get. Okay, this is called ACE, area control error. This is what PJM uses to get all that together. So it's just a big balancing act. So that's what I'm trying to get through to you. Is this is an ongoing 24/7 real-time thing to keep everything balanced. And you can't do it with renewables. Not at this point in time, not with this level of technology. I hope we can. It'd be a great thing. I mean, no one wants to pollute the earth. Really, we don't. but the price for power is the price for power. Um, we have a relatively low price for power in the United States. It's not bad at all compared to many other places in Europe. Um, and then power, good stable electrical power, is what gets people out of poverty. You can't have a manufacturing basis without stable electricity. You can't make widgets, things, without stable electricity. Your third world countries that are striving to become more industrialized so that they can be that cheaper manufacturing location to get things made at, they have to have stable power first. Can't do it without it. It's just that simple. You can't mass produce shoes, widgets, light bulbs, blenders, car parts, tires without stable electricity. You can't make glass. I mean, the things everyone takes for granted. So this is what's going on. Like I say, this is real-time data. You can go New York ISO, go to just Google NewYorkISO.com, PGM.com. That's the Northeast. That's almost the entire Northeast. You can just Google the power grid, and you can see what the Western interconnection, the ERCOT, the Eastern interconnection, and what it's all made up of. All of them have websites. It's all public information. It's not something super secret. So the next time you hear someone try to tell you that everything can be done from wind, I'm sorry, it physically can't happen. If it were free tomorrow and unlimited tomorrow, it still would take years and years and years to get it built up enough to where it could be on the grid and be useful. So again, it's a fact. This isn't anything that's even arguable. And when you hear the pundits talk from one side or the other, none of them will talk about this because it's not pretty, it's not sexy, it doesn't sell newspapers, it doesn't sell print time or TV time. So we're working on it. All the utilities are working on it. Everyone in the power industry is working toward getting stuff that doesn't pollute as much, stuff that's more renewable, stuff that doesn't hurt our planet. But you can't worry about something that's going to happen hundreds, if not thousands of years down the road and cut your nose off to spite your face today to fix it. You can't fix it today. And there are many, many, many who are environmentalists that say we can handle the climate change issues. Will cause problems, yes, but those are things we can fix as they happen later on. It doesn't mean you give up and not try to do things cheaper, lighter, cleaner, better now for the environment. But again, you don't go overboard and cut your nose off to spite your face. You have to have power, period. Without electricity, our entire society stops as we know it today. Now, if we're using our own fuel to generate the electricity to keep ourselves independent from those who don't like us, that should be the way to go. I mean, we have abundant natural resources. So, again, don't let ideology override reality and facts. So, I know I was a little bit long-winded. This is still less than an hour. So, in less than an hour, you have a concrete, fact-based reason why a lot of what you're being told on the news is 1,000% a lie. It's an out-and-out lie. You cannot replace fossil fuels with renewables, period. Can't be done. 20% versus 60% of the grid. Can't make it from here. Yes, like I said, if you are, get candles. Better, stock up on some wax and, sell candles. You'll make a lot of money because that's the only way you can do it. You have to turn the grid off at night and burn candles. I don't know. So, again, we want a reliable, stable grid. You have to have voltage support to do that. Wind and solar at present do not give anywhere close to what's needed. This physically, they do not provide it. I hope that we can get it. It'd be nice. So look at these websites and look at facts. Don't listen to pundits. Don't listen to ideologues. Don't listen to political rambling. Look at these websites. This is the real world right now, in PGM's footprint, in New York ISO's footprint. Go to Texas and look at ERCOT, is the power management for Texas, is ERCOT. Look at the Western Interconnection, the different utilities in the West Coast, and guys, I'm not making, this is, like I said, this is facts, real time data as of right now, 3:23, and it's almost 7 in the morning. So here's your load forecast. This is the load curve. So today, 8 p.m. There's 8 p.m. There's a lot of information out here, and you can. This is what, and PGM is pushing hard to get more renewables. New York ISO is pushing hard to get more renewables. Again, the people the guys that are working in the background to provide power, we want everything to be as renewable as possible. Again, no one wants to kill the earth, but it's not at a 4-alarm fire stage as many people would like to think that it is, would like to tell you that it is. All the projections are 10, 20, 30 years out, and so far none of those projections have ever been correct. The guys in the 80s that were projecting by 2000 we would have catastrophe were wrong, dead wrong, not even close, not even the same ballpark. In the 90s, same thing. 2000, the same thing. Every one of those model projections that are talking about doom and gloom are wrong. 1,000% wrong. Not even close to being right. So please look at real facts. Don't just think that we can do it on hope and a prayer. Can't happen. I will get off my soapbox now. Again, facts. I deal with this. This is my job. I deal with it every day. I look forward to the day that we can have, Mother Nature use the sun to be able to give us what we need for power, for electricity. That would be a great thing. And I hope it can happen, but it won't happen anytime soon. So keep an eye on your new technologies, new industries. There is a great and a safe, let me say that again, a safe level of reactor coming out. And you can go to the U.S. Energy's website. It's TRIS. There you go. TRISO. Coated fuel particle. Department of Energy. www.energy.gov. What they've done is they've taken a uranium pellet, coated it in 3 layers of ceramic coating. It's called a TRISO particle. This particle can withstand more than 1800 degrees Celsius, which is over 3000 degrees Fahrenheit, which is well above the maximum heat generated in a nuclear disaster, as far as what the term, and I hate the term meltdown because it doesn't melt, but in a nuclear, where the fuel cell breaks, let's put it that way, the heat generated in that accident is far less than this 3000 degrees Fahrenheit. So what it basically boils down to is each one of these particles, if this fuel, this uranium inside, had a catastrophic failure, the heat generated would not be enough to break this coating. So in other words, it is 100% safe. These are what's called a Gen 4 reactor. The 2 companies, X Energy and Keros Power, are doing these tests now, currently. Right? This is the design. This is one of the designs. There are a lot simpler reactors. They can be scalable because you can have that small TRISO particle I showed you. This can be as small as basically a little bit bigger than a seed, right? And they make bigger ones that can be the size of like tennis balls, softballs. And all you need to do is have multiple little pellets or little balls inside the reactor. They use gas. There's a couple different mediums that they use to cool the reactor. And you can go to this website and look, but it's scalable, so they can have it small enough that it could be on the bed of a truck, the entire nuclear reactor, and all support in the bed of a trailer. Now, you could do that for like a military application, like to power a military base where there's no power before. You could do a small city, a little town like where I grew up, a little tiny 4,000 person town. You can scale them a little larger. It's totally scalable. Um, See, there's your pellets all inside. You have your coolant flowing around them to keep the coolant around. Your heat that's generated from the nuclear reactor goes into a steam generator of some type that boils water and turns it into steam, and the steam is taken, piped off to turn turbines to make electricity. Like I say, nuclear power isn't that complicated. It's just a $300, $400 million or $1 billion hot water heater. It just never needs to be plugged in. Once the fuel runs out, you put more fuel in. Now with this design, you literally can flush out fuel and add more to it. I mean, it's an awesome technology that's using nuclear power, which is totally green, no pollution whatsoever from nuclear power, because again, it's just boiling water. And with these Triso particles, you don't have to worry about the waste. It is safe to transport to where you could put it in the salt flats out in Utah. I think it's Utah, that was designed to put all our nuclear waste until the problem of transporting the waste from active reactors became a political football and hot potato. With this type of technology, there is no danger in transporting it from wherever the reactor is to those places that could store the waste. And again, they're talking, the scale is unimaginable. If you're not in the industry, you can't imagine how much power you get out of uranium and nuclear reactors. So, like I said, that's just the one company. The other is the Keros Power. They use a slightly different medium for cooling the reactor. They use a liquid salt, where the other uses a gas. But here's your reactor with your Triso particles. You're using salt to moderate the reactor and to cool it, absorb the heat, take it out. They run it through a heat exchanger. Then it goes into a steam generator where the heat goes through the coils. This is at a higher pressure to maintain it, to keep the heat in. Around the coils are just water at atmospheric pressure. The heat passes through the tubes, just conduction, flashes this to steam. Steam goes to a turbine. The turbine generator makes electricity. It goes off to the grid. Then the steam gets condensed, made up feed water, like from a lake, from whatever your water source is, pumps it back into the steam generator to start the cycle all over again. This goes back into the reactor heats it up, cycle. Just a vicious, you give up your heat into the steam generator to make steam, then you put the water, pump it back in, this goes back in at a lot cooler temperature, it absorbs the heat from the nuclear reaction, the heat goes back in, you exchange heat, exchange water, boil steam, boil water into steam, pump the steam, turn the turbine, make electricity. It's just a vicious cycle, over and over and over again, 24/7. But the scale is insane. You can't imagine, like, the current reactors. We have reactors that run 1,000 megawatts, 1,500 megawatts, 1,200 megawatts, so 1,000 megawatts is rounded down. Now, how many turbines at 2 megawatts per turbine would you have to have in a wind farm to create just one nuclear power plant? So, and I'm sorry for the background noise. That was the heater kicking on. I'm sure you heard it. But guys, this is some of the future of nuclear power that is taking safety to unbelievable levels, taking the waste part of the nuclear waste part of the equation that inflames such passions, and adjusted to where that's not an issue anymore, really and truly. It's scalable. You can go as small as enough to power a small facility. You could scale it up to a small town, scale it up to run an entire larger city. You could put these in multiple places, making the transmission grid change as we know it. You wouldn't need necessarily to do a lot of transmission lines if you had these all over the place. You could put them closer to the load where you didn't have to transmit as much power and transport it. Like I said, there's a lot of technology with this, so again, don't be closed-minded with new energy. There's a lot of things besides wind and solar. Now, I hope we can get wind and solar much more efficient, get batteries that are much more efficient and less in cost. But when you talk about solar, you have to talk about batteries. So when you're looking into environmental aspects, look into what it costs and what environmental things it takes to make a battery. A lithium-ion battery has a lot of natural resources that get used, a lot of mining, there's a lot of waste, there's a lot of environmental issues with getting the materials you need to make a battery. So don't forget about that too. So again, nothing is one-sided. There's always two sides to the coin. There's always a counterpart to the benefit. There's a con to the pro. So I'm just urging you to look at things through a bigger picture, through a more larger lens, so that you're not duped into one part or another. There's no perfect solution yet. We're working toward it. There's a lot of smart guys and gals that are doing a lot of smart things to make things better and to help get us to a clean energy future. So we can still work toward that and use resources we have that are abundant now. We're much better than we were 10 years ago, which is light years better than we were 20 years before that. The pollution levels are far, 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 far less than what they used to be. Is it perfect? No. And we're moving toward that. So I'm pleading with you is to look at things through the real world and look at the whole picture, not just this. Don't be the magician that's waving over here and not seeing what his other hand's doing. Okay? So when you hear a politician tell you that we're going to have all of our energy from renewable energy and no coal, no fossil fuels, it's a lie. You can't do it. Physically impossible. And that's a fact. This isn't an opinion. This is fact. So take that. I hope you could take that with the evenness that it is meant. Again, I'm not advocating one to the other. And just while we were talking a little bit ago, we were in the $20 to $40 range. This is PGM footprint again. Now the price for power, again, as the day picks up, we're now a little after 7 o'clock, not at 6 o'clock. The price for power has gone up. Now it's $40 to $70 per megawatt hour for the entire footprint right now. Not 20 to 40. This changes throughout the day. Again, and these are the independent zones within this area. AE is Atlantic Electric, AEP is American Electric Power, APS is Appalachian Power, ATSI is, that's a kind of a conglomerate. That's ComEd is around Chicago, Dayton Power, you got Dominion Power, DPL is Dayton Power and Light, Duquesne, DUQ is Duquesne Power, that's around Pittsburgh, EKPC is Eastern Kentucky Power, JC is Jersey Central, ME's MedEd, Jersey's obviously Jersey, MedEd's in the middle of Pennsylvania there, OVEC, PE, PEPCO, PGM RTO is the whole PGM footprint. This is like an overall average of the entire PGM area, right? PL's, it should be PPNL, it's Pennsylvania Power and Light. PN's Penelec, PS is Public Service, that's in Jersey. Penelec is in Eastern Pennsylvania. So that's these are the different entities within the PGM footprint, and they have their own different power points. Like I said, this is an overall average giving you this. This is the independent. So Public service, which is in New Jersey, is $28.94 per megawatt hour is their location, their LMP right now. Again, this all will change. Let's do Dominion. So through Virginia, Dominion Power is $31. So they're $3 more than the New Jersey Area Public Service. So there's your different prices. And like I said, that changes constantly throughout the day. Depends on what outages are happening. Depends on if something breaks or if something's just taken down for maintenance. Generators have to come offline to do their maintenance items, to refuel, like nuke units refuel. They have tube leaks they have to fix within the steam generators. They have all their auxiliaries that keep the plant running. That they can have outages with that. That's where it can't. The pumps don't work, where you can't get feed water into the generators to make the steam. It's an incredibly complicated process, but any outages, whether it's planned or unplanned, can change what this price for power is throughout the footprint, and that changes throughout the day just with loading. As you can see, the loading's going up, and that changes the price for power. At night, when you don't have a high demand, when the load is low, price for power goes down. Supply and demand. So it's literally just that simple. So look at these resources before you jump to conclusions and bash fossil fuels to the extent that they're evil 100%. They're not. And wind and solar's the white knights with the angels on their wings, and they're all good, and then they're not. Everything has a blend. Everything has a mix. Look at the real world, please. That's what I'm begging you. So take a balanced approach. Don't cut your nose off to spite your face, and get real information, the whole story, not just the bits and pieces, and not the glamorous and the nice stuff. So look at the bad stuff too. Then make your decision, and call your politicians, your elected officials, and tell them to quit lying to you, because that's what they're doing. And honestly, they don't have a clue either. They're not part of this industry. They don't know. They're going by what brief was prepared for them by what staffer, and they have a general direction that's politically inclined most of the time. So it's weighted to kind of prop up their part of the story. So get the real information. Look at, and again, look at all this information that's here. There's markets and reliabilities. There's relief efforts, the different filings for the NERC and FERC, which are the governing bodies over the entire grid, over the entire electrical industry, the energy commissions that are in the local areas. Look at all of this. One of the things and I know I'm rambling, I'm sorry. One of the things that would be a huge help is the reactive power component that I talked about before. Here's a reactive power compensation task force. Right now, generators do not get paid to provide reactive support. They get paid for megawatts and megawatts only. It's in their best interest. They have to stay up, so they have to do some sort of reactive support. But if they were to be able to be paid for reactive support, that could spawn a whole new industry that would give generation support. So other devices that aren't necessarily generators, you have things called synchronous condensers that don't provide power as far as megawatts. They provide reactive power only. Older generators have been decommissioned that are no longer viable to run from a megawatt perspective, can be converted into synchronous condensers to give us voltage support in areas that are weak in that. There are devices called SVC, static var compensators, which use inductors and capacitors on solid state equipment to provide reactive support in key areas that are historically bad for voltage in those areas. Again, it's more than you want to know, and it's boring probably to most of you, but there are other things out there. But again, it all boils down to cost. If you're not getting paid for reactive power, then who cares if you produce it or not from that generator's perspective? They get paid for megawatts, for real power. So they have to do some reactive support, but it'd be nice if there was a reactive compensation for generators. Then maybe they would make their generators, the design of them would change to give more voltage support. And that gives more stability to the grid, less blackouts, less issues when you have that voltage to prop up the grid and push power from the generation to the load. That's it. Thank you. I'm sorry I took up a long time.